Hi everyone, welcome once more to Best Science Brain YouTube channel. Today we're taking another chemistry content from general chemistry first year undergraduate students and also for students that are doing the A-level courses, just like the JUPEB program, Joint Universities Preliminary Education Program course meant for students or intended undergraduates. So that after this program, they can move to the second year in the higher institution in Nigeria. Then also, this program is not only meant for Nigerian schools, as our YouTube is global, so also meant for students in other higher institutions or tertiary institutions, first year in the universities, polytechnics, or colleges of education. Then also, this topic we're going to treat also is meant for people writing during the A-level program and those in their final years of O-level program. That is final years of secondary school or high school per se, which is the term used to ascribe, which is ascribed secondary school in Western world. So you're welcome to this online lecture. This is your YouTube moderator, Dr. B. And also, if you are seeing the channel for the first time, or if you're not a subscriber to the channel, the video is playing, you look at the dots, the three dots beneath the video, tap on those dots, you see some icons displayed, then tap on subscribe, on subscription, and get subscribed to the channel. If you already subscribed to the channel, you don't need to subscribe again. Share our videos to students that need it. Share it to WhatsApp group and then of students in high institutions that first year or general chemistry. Particular video, we still have video for students in higher levels of higher institution, quite all right. So having done that, today we're going to introduce the mole concept, the mole. What do you understand by the word mole? When the chemists use the word mole, the mole is more like a counting unit for the chemist, a counting unit in chemistry. Just like the way you count your money in naira, you count your money in dollars, you count your money in pounds. The chemists count in moles. Just like a market woman sells gari in cups of gari, or it sells rice in cups of rice. The mole is also similar to that concept, the counting unit for chemists. The mole is not measurable, as you cannot weigh it by gravimetric analysis. You don't use that instrument to weigh the mole. Rather, it can be quantified, it can be calculated, or it can be obtained from mass and other relationship in chemistry. So in chemistry, we define the mole as the mole is the amount of substance that contains as many elementary particles. These particles include ions, molecules, atoms, or even electrons, as there are carbon atoms in 12 grams of carbon-12 isotope. So let's repeat the definition again for the mole. We say the mole is the amount of substance that contains as many elementary particles, which could be ions, molecules, atoms, or electrons. There are carbon atoms in 12 grams of carbon-12 isotope. So let's try to explain this a little. Let's assume that we have a cup used for measuring rice. So as I said in a previous illustration, that the market woman can use cup for measuring rice. Maybe you want to buy 5 cups of rice, you have a standard, which is the cup she uses. And this cup is filled with grains of rice. With grains of rice. So now, let this cup be taken as 1 mole. Let this cup be taken as 1 mole. And let the grains of rice be taken as a chemical substance. Perhaps the grains could be element, the grains could be compound, the grains could be gas. So let the grains of rice be taken as a chemical substance. The question is this: if these grains represent the chemical substances we have in bracket, how many grains of rice will make up 1 mole? How many grains will make up 1 mole? So, I made a mistake. Sorry, the grains represent the particles that is the atoms. Sorry, the atoms, molecules, the many particles in 1 mole as we defined, not element compound. So, I could repeat myself. Let this cup represent 1 mole of a substance. The grains of rice in it represent the elementary particles in a mole, which could be atom, molecules, ions, or even electrons. The question is this: how many atoms will fill up this rice to make up 1 mole of an element? Take any element, for instance, like a metal like sodium, iron, potassium, copper. So how many atoms of copper will make up 1 mole of copper? Do you understand it? So how many atoms will fill up this cup if the atoms are now equated to the grains of rice? If rice now represents sodium or any element like iron, so how many grains will make up 1 mole? We're told that 1 mole will contain 6.022 times 10 to the power 23 particles. So for me to have 1 mole of any element filling up this place, let's say sodium or potassium or copper or carbon, I need these particles, this particular number of particles of the atoms to fill up this cup. So 1 mole of sodium contains 6.022 10 to the power 23 atoms of sodium. 1 mole of iron contains 6.022 10 to the power 23 particles of iron, an incredible number. So you see that. So that means if this truly rice is 1 mole, that means a cup of rice should contain 6.022 10 to the power 23 grains of rice. Okay? Then, if we're talking about gases, because gases exist as molecules, a gas like oxygen, hydrogen, chlorine, nitrogen, CO2. These are gases. Then, if this cup is filled with any of these gases, then the question is this: how many particles of these gases will fill up this for us to have 1 mole? The same number we still need 6.022 to the power 23 molecules of oxygen to make up 1 mole. We still need 6.02 to the power 23 molecules of hydrogen to make up 1 mole. We still need 6.02 to the power 23 molecules of chlorine, nitrogen, carbon further to make up 1 mole. So for 1 mole of an element, you need this number of atoms. For 1 mole of a gas, you need this number of molecules to have 1 mole. That is it. Then, if we have a solution like sodium chloride dissolved in water, gives you sodium ion and chloride ion, having ions of sodium and chloride. So if this solution fills up this cup, how many particles of the ion will make up 1 mole of this solution? We need also 6.002 to the power 23 sodium and chloride ion to make up 1 mole of sodium chloride solution. So the mole is like an abstract idea, but you have to understand it. That for you to say 1 mole of a substance, the substance, it could be made up of atoms if it's an element, it could be made up of molecules if it's a gas, it could be made up of ions if it's a solution. But for you to have one more or any particular substance, be it element, gas, or solution, you need this number of particles to make up one mole of that substance. This number is called the Avogadro's number. You call it the Avogadro's number, or you can call it the Avogadro's constant. You see, the Avogadro or Amedeo Avogadro is an Italian lawyer that later developed interest in mathematics and physics and became later on a professor of maths and physics. So you can wonder, somebody that was a lawyer before, then developed interest in sciences. So Avogadro did, but you have to know that Avogadro did not introduce this number. No. Even though this number was named in honor of him. So the man that introduced this number is called Jean Perrin, a French physicist. Introduced number. He was the one that obtained this number by mathematical and experimental derivation, not Avogadro himself. And then he named it to give respect to Avogadro. So Jean obtained this number in the year 1926, around that period, and he won a Nobel Prize for obtaining the Avogadro's constant. Although Avogadro is remembered for his Avogadro's law or Avogadro's hypothesis in chemistry under gas law, but he did not give the number which called Avogadro's constant. So that is wonderful. So science has histories or deals with history. So having done that, we now have to introduce the concept of what called molar mass. So what do you mean by molar mass of a substance? The molar mass, we say this is the weight of 1 mole of a substance. That substance can be a compound. So compounds have molar masses. The weight of 1 mole of a substance. The unit of molar mass, the SI unit of molar mass, is what's called gram per mole. It's expressed in gram per mole. That is, look at the unit, gram per mole. So for example, if I have sodium chloride, I want to find its molar mass. I'll be given the atomic mass of sodium as 23 and the atomic mass of chlorine at 35.5. So to find the molar mass of sodium chloride, let me call it mm, what I'll do is I will add the atomic mass of sodium to chlorine. Sodium is 23, chlorine is 1 atom, 35.5. That gives me 58.5 gram per mole. Meaning that 1 mole of this substance called sodium chloride weighs 58.5 grams. You see, that is why we say the molar mass is the weight of 1 mole of a substance. If I have this substance called copper sulfate, I want to find the molar mass. I'll be given the atomic mass of copper, 64, atomic mass of sulfur, 32, oxygen, 16. To find the molar mass of copper sulfate, I'll add the relative atomic mass of the different elements as they occur. Copper is 64, sulfur is 32, oxygen is 16, multiplied by 4. Why did I multiply by 4? Because there are 4 atoms of oxygen in the compound, but copper is only 1 atom, I wrote 64. 1 atom of sulfur weighs 32 grams, oxygen 16. Because of 4 multiplied by 4, when I solve everything, I'm going to get 160 gram per mole at the molar mass of copper sulfate. If I'm given maybe a compound like Al2SO4 bracket 3, I want to find the molar mass of this compound. Very simple. I'll be provided with the relative atomic masses of aluminium, sulfur, and let me take it up here. Aluminium 27, sulfur 32, oxygen 16. Then I have Al2SO4 bracket 3. So how do I evaluate the molar mass? So if you look at aluminium 1 atom weighs 27 grams, but there are 2 atoms here, and I say 2 times 27. So for the 2 atoms. Then the bracket, and I say plus and open the bracket. Then sulfur 32, I write 32 for sulfur. Oxygen is 16. Here, multiply by 4 because of 4 atoms in the bracket. These 4 affects only oxygen, it does not affect sulfur. Sulfur remains 1 atom, 32. Oxygen 16 times 4. Then close the bracket and multiply by 3. The 3 outside the bracket. Then that gives you 54 plus, add up what you have in the bracket. 3 times 4 times 6 is 64. 64 plus this give you 96 multiplied by 3. You solve everything, you're going to have 342 gram per mole as the final answer. So that's the molar mass of that compound. So you see, that's how you get molar mass. Then for molecules like oxygen, gases are diatomic in chemistry. Gases are that we call them homonuclear molecule. That is molecule made up of similar atoms. So oxygen, nitrogen, what again, and so on. We want to find the molar mass. The atomic mass of oxygen is 8. So the molar mass of oxygen is going to be 8 times. Atomic mass of oxygen is 16. Sorry, the molar mass becomes 16 times 2. That gives you 32 gram per mole. Chlorine, the atomic mass of chlorine is 35.5. The molar mass of chlorine molecule becomes 35.5 times 2, give us into 1 gram per mole, and so on. So we often hear of relative molecular mass. Relative molecular mass. Is there any difference between molar mass and relative molecular mass? There are no more difference between the two. Only that relative molecular mass is expressed as a ratio of carbon-12 isotope. So, relative molecular mass in chemistry is defined as the number of times the average mass of one molecule of a substance is heavier than 1/12 of the mass of one atom of carbon-12 isotope. So we'll say defined as the number of times the average mass of one atom of one molecule, of a substance is heavier than 1/12 of the mass of one atom of carbon-12 isotope. So this is the way we define relative molecular mass. So in terms of quantity or value, there are no more difference. If the molar mass of a compound S is 100 gram per mole, then the relative molecular mass of the same compound S be equal to 100. You see that the molar mass of a substance and the relative molecular mass are equal to each other. The difference is that the molar mass is given a unit, while the relative molecular mass has no unit, because the ratio of the mass of a substance and the mass of carbon-12, the units will cancel each other. So you see that the two of them are equivalent to each other. So having done that, we're now going to the calculations involving number of moles. Before we go to the calculation involving number of moles, how do we define the Avogadro's constant? We mentioned the Avogadro's number today. We said that the Avogadro's constant introduced by Jean Perrin is 6.02 approximately 523. So if you have defined Avogadro's constant, you say the Avogadro's constant or number constant is the number of elementary particles which could be atoms, ions, or molecules present in 1 mole of a substance. The number of elementary particles, which could be atoms, molecules, or ions present in 1 mole of a substance is called the Avogadro's constant. Now we'll go over the calculations on number of moles. So let's move. So there are a lot of formula to calculate the number of moles present in a given substance. So we're going to introduce about 5 to 6 formula in this video to obtain number of moles in a given substance. I'm going to take them one after the other. When we introduce each formula, we'll take examples of calculations before we go to the next formula. The first formula we're going to look at is number of moles, which is N, given by M over AM. We'll call this our equation 1. So where M is the mass of the substance, and then this AM is a short form for relative atomic mass of the substance. So that is the first equation we're introducing. So when we use this equation is used. Equation 1 is used for the first all metals, because metals exist as monatomic atoms. All metals, know your metals: sodium, lithium, potassium, calcium, magnesium, aluminium, zinc, chromium, platinum, gold, iron, and so on. All metals, because you cannot write the form of a metal as Na2 or Li3. Metals are always exist as monatomic elements, so they have atomic mass, not molar mass. So then you also use this equation for certain nonmetals. Certain nonmetals, examples include carbon, sulfur. Okay, also use it for all metalloids. Metalloids include example silicon and boron, elements that have properties of both metals and non-metals. So arsenic and so on. Then which other example, when do I apply these ones? They exist as monatomic elements in most cases, in all cases. Then we also have noble gases or noble gases. You know, in chemistry, noble gases are unreactive. They cannot form molecules. Example: helium, neon, argon, xenon, krypton. So these elements are associated with atomic masses, not molar masses. So when you want to find the number of moles and the mass is given to you, you use that atomic mass. They don't have molecular mass or molar masses. So let's take some examples now. So the first question says, calculate the number of moles present in 80.2 grams of sulfur. So the mass of sulfur given to us is 80.2 grams. The relative atomic mass of sulfur is 32. We're looking for number of moles. And sulfur is one of the elements we mentioned that is monatomic in its nature. Unless you are talking about rhombic sulfur, allotropes of sulfur, not about atomic sulfur. But since the question does not specify that, we take sulfur as being monatomic. So number of moles here is given by mass over atomic mass. So we now have 80.2 over 32. If I have 2.51, then moles, because the value is more than one whole number. 2.51 moles of sulfur. So look at it in a jiffy. We'll go to the next question. We'll go to question number 2 that says, calculate the amount in moles, which is seen as number of moles, present in 1 pound of aluminium. The aluminium atomic mass is 27. Then 1 pound weight is 454 grams. So having done that, we now look at the mass of aluminium, which is 1 pound. But in chemistry, masses are expressed rather in grams. That's why you're doing the conversion here, because atomic mass is weighted in grams. So that's why they give the equivalent. So you convert, that becomes 454 grams. Then the atomic mass of aluminium is 27. It's a metal. So being a metal, we expect it to be monatomic. We don't have to find the monomass. So you don't have to go and do aluminium. This doesn't exist and say 27 times 2. No. So it remains atomic mass is the weight of aluminium, monatomic. So N becomes mole over atomic mass, which is 454. That is the mass converting to grams all over 27. That gives you 16.8 moles of aluminium present in 1 pound weight of aluminium. The next question says, how many grams are contained in 2.5 moles of aluminium? So you get the number of moles already. So your N is 2.5 moles. How many grams? What had the unit of gram? The value you're looking for is mass, of course. And they gave us that mass of aluminium as 27. So this time around, you're not looking for mole, but the formula is also useful, and equal to mass over atomic mass. You now make mass the subject. The denominator of this mole is 1. You cross multiply. So m times 1 gives us m. The mole times atomic mass. That gives us 2.5 substitution times 27 to get the mass of aluminium. So when we solve this, the mass of aluminium we obtain is 67.5 grams. 67.5 grams of aluminium. So that's the answer to the question. So we'll go to the next exercise. Let's look at the question on the board that said a cylinder contains 25.4 mil or milliliter of mercury. If the density of mercury is 13.534 gram per cm cube, how many moles of mercury are in the cylinder? And you're giving the atomic mass of mercury as 201. So look at the equation. We're looking for moles. Well, we know that mercury is a metal. And being monatomic, number of moles should be mass over atomic mass. Before we go ahead, we don't know the mass. We have to find the mass first. What we are giving here is the volume of mercury. That is volume 25.4 mil. We is entered as 25.4 cm cube because 1 milliliter is equal to 1 centimeter cube. We also given the density of mercury. The density again as 13.534 gram per cm cube. So that's the density of mercury. So we have to find the mass of mercury first using this information given to us. From your physics or from your knowledge of physical chemistry or physics, you know that density is mass over volume. Make mass the subject. Mass becomes density times volume. Density is 13.534 gram per cm cube multiplied by volume, which is 25.4 cm cube. Cm cube cancels cm cube, so the mass will now be in grams. So if you multiply the values, you're going to have 344 grams as the mass of mercury. So since the atomic mass is always expressed in grams, we can now find the number of moles by dividing 344 by the atomic mass of mercury. That becomes mole becomes 344 by the mass which we obtained there over 201, which is the atomic mass of mercury. Solving that, we'll get our final answer as 1.67 mole of mercury as the answer. So now we have exhausted the first formula. We'll now go to the next formula for finding number of moles. So we have equation 2 on the board, which says number of moles equal to m over mm. M still stands for the mass of the substance. Mm is the molar mass or the molecular mass or relative molecular mass of the substance. Then when we use equation 2 is used for mainly homonuclear molecules. Homonuclear molecules or gases. so which include oxygen, they are diatomic. Nitrogen, molecules that are made of similar elements, they're already diatomic. So gases are diatomic except the noble gases that are monatomic, which we consider in the previous situation. Then bromine, iodine, even though it's a solid, and so on. So all these are homonuclear molecules. Then we can still use it for heteronuclear molecules. That is molecules or gases made up of different elements like CO2, ammonia, methane, different elements. They can have molecular masses. So in this case, you don't talk about, they all have molecular, both mononuclear and heteronuclear have molecular. You don't talk about atomic mass for them. Then we can still use it for compounds because compounds have molar masses. Example, sodium chloride, H2SO4, potassium chloride, copper sulfate, copper nitrate. All these are compounds containing different elements joined together. So all these compounds, these substances can either have molar mass or relative molecular masses, which you need to calculate before you apply the formula. So let's take some examples now. So let's look at the question on the whiteboard that says calculate the number of moles present in 3.2 grams of oxygen gas. So look at this question. We're looking for number of moles, which is N. Then the mass of the gas given to us is 3.2 grams of oxygen gas. Oxygen is diatomic, so we look for the molecular mass of O2. It's not monatomic. That becomes 16 times 2 giving us 32. Number of moles becomes mass over molecular mass or molar mass, which is going to be 3.2, the mass of oxygen, over 32, the molar mass, and that gives you 0.10 mole of oxygen gas as our answer. Go to the next example. Question on the whiteboard says, what mass of H2SO4 are there in 0.25 mole of the compound? In the equation, we're looking for mass. They'll give us number of moles. The substance given to us is a compound containing different elements. So we have to find its molar mass. We have to calculate the molar mass of this acid. So hydrogen is one atom. We have two atoms. So two, and the mass of hydrogen is one, sorry. The mass of hydrogen is one, but there are two atoms, 2 times 1. Sulfur is one atom. The mass of sulfur is 32. Oxygen is 4 atoms. The mass of oxygen is 16 multiplied by 4. That gives us 98.0 gram per mole as their molar mass. So we're looking for mass. Relationship is N, that guides the three of them. Mass over molecular mass. We make mass the subject by cross multiplying. So mass becomes mole times molar mass. The value of the mole is 0.25. Our molar mass is 98. So multiply 0.25 by 98, we get 24.5 grams of H2SO4 acid as our answer. Move to the third example. Look at the question on the board that says 0.125 mole of a compound weighs 32.25 grams. Calculate its molar mass. The first thing we ask ourselves is what we're looking for. We're looking for the molar mass of the compound. So this is the number of moles, and 0.125 mole. The mass of the compound is 13.25 grams. Looking for the molar mass. It's very simple. Mole is mass over molar mass. You make molar mass the subject by cross multiplying. So now I have mole times molecular mass equal to mass. So you want this to be on one side. You have to cancel off n. Divide both sides by n. So n cancels n. So molar mass becomes mass over mole. The value of our mass is 13.25 gram. and then our mole is 0.125 mole. Also have 106 gram per mole as our answer. Had it been that we are out to find the relative molecular mass, the answer would have been only 106 without any unit. But since we're looking for molar mass, how to put the appropriate unit. So go to the third equation for finding number of moles. We exhausted the first and second equation. The first was mass over atomic mass. Second was mass over molar mass or molecular mass. So the third equation is displayed on the board. Number of moles equal to CV over 1000, equation 3. Or number of moles equal to C times V. Look at equation 3 in two alternative form. CV over 1000 and equal to CV. So when do we use the first form? Use the first form when the volume is expressed in centimeter cube. Use the second form when the volume is expressed in decimeter cube or liters, because 1 liter is equal to 1 dm cube. That equal. So you should know that. Then, when do I apply this formula? Is when we are looking for a number of moles of a substance that is in solution, that dissolve in water. So where C is called concentration with unit mole per dm cube, and V is volume of solution. So C is concentration. Concentration refers to the quantity of a substance or the amount of a substance in 1 dm cube of a solution. The amount of a substance in 1 dm cube of a solution, that is what's called concentration. So you see that if you look at this formula, is that N is CV. Okay, from here, the unit of concentration is mole per dm cube. You see, mole, then the meaning of that, P means all over. Then the volume is expressed in dm cube. So that dm cube cancels dm cube. We're left with mole with the unit of this quantity N, the mole. But that is why we have to divide by 1000 if this is in cm cube. That 1000 convert the volume to dm cube before we solve. So when the V is in cm cube, there will be 1000 under. When the volume is in dm cube, you don't divide by any 1000. We go to the next question. So let's look at this question on the whiteboard. Calculate the number of moles present in 250 cm cube of 0.1 molar H2SO4 acid solution. So we're looking for number of mole, which is N. Volume is 250 cm cube. This 0.1 molar is the concentration. So when you see 0.1 m, it's taken as 0.1 mole per dm cube. So this unit and this are the same. So looking for number of moles. So the formula connects N, C, and V is N, C times V. But because the fact the volume is in cm cube, we have to divide by 1000 to convert it to dm cube. So that becomes 0.1 times volume 250 over 1000. Also, we're going to have 0.0250 mole as our answer. So look at the next question on the board that says calculate the number of moles present in 3 dm cube of 0.05 mole per dm cube sodium carbonate solution. Number of moles is what we're looking for. The volume is of the solution is 3 dm cube. The concentration of the solution is 0.05 molar or mole per dm cube. So you're looking for the number of moles that connects, the formula that connects these three items is N equal to C times V. So this time around, are we going to divide by 1000? No, because the volume is in dm cube. And this is in mole per dm cube. So that will now have 0.05 times 3. That gives us 0.150 mole as our answer. So having done that, go to another exercise on this. So we have another example on the board that says calculate the concentration of a solution containing 0.01 mole of H2SO4 in 250 cm cube of solution. So we're looking for concentration. The sample concentration is C, that is molar concentration. This is mole, that is your N, 0.01 mole. Distribute between mole and concentration. When you have mole, that is N. When you have mole per dn cube, that is concentration. So volume is 250 cm cube. Looking for concentration. The formula that joins them together is N equal to CV. I'll divide by 1,000 because of the unit of the body, which is cm cube, which I explained earlier on today. So what I do? I'm going to make C the subject. First, I'll cross multiply. So CV times 1 gives you CV. N times 1,000 gives you N times 1,000. Make C the subject. Divide both sides by V so that C be on one side. So our C becomes N times 1,000 all over volume, because V cancels V. The value of our N, number of moles, is 0.01 mole times 1,000 all over. The volume is 250. So when we solve, our final answer is 0.040 mole per dn cube, or 0.040 molar solution. So that is the answer to the question. So having done that, we now go to the fourth formula of finding number of moles. We have done three formulas: N mass over atomic mass. Second, N equal to mass over molar mass. Third, N equal to CV, or CV over 1,000. So we look at the fourth formula that says number of moles equal to NS over NA. So what do these symbols stand for in this formula? Our NA, the denominator, is the Avogadro's number, or Avogadro's constant. Being a constant, the value is known, 6.02 times 10 to the power 23 particles. And then NS, which is this, is the number of elementary particles. Those particles that make up 1 mole, which could be atoms, molecules, or ions. Then from this formula, I can still make NL, so NL becomes number of moles times Avogadro's constant by cross multiplying. So this formula is somehow broad. That is, you can use it to find number of atoms. If you look for atoms, S becomes number of atoms. If you look for molecules, S becomes molecules. If you look for number of ions, S becomes ions. So let's see how we're going to apply this formula in calculations now. So let's go to this formula on this question on the board that says calculate the number of atoms present in 10.8 grams of silver bracelet. The atomic mass of silver is 108. The Avogadro's constant is 6.02 times 10 to the power 23 atoms. So I repeat, it says calculate the number of atoms present in 10.8 grams of silver bracelet. So we have the values we need given to us on the board. The atomic mass of silver is 108. Avogadro's constant is 6.02 power 23. So in this question, we're presented with the mass of silver bracelet, or silver bracelet, 10.8 grams of silver. We're given the atomic mass of silver, and silver is a metal, monatomic element. So find the number of moles in this 10.8 grams using mass over atomic mass of silver. That becomes 10.8 over 108, giving us 0.10 moles. So this is the number of moles of silver present in 10.8 grams of silver. But we are not looking for number of moles, we're looking for number of atoms. Remember I told you the number of atoms, which is NS, here S stands for atoms, is now number of moles times Avogadro's constant. So multiply the number of moles you got from there, 0.1 times 6.02 power 23. 0.1 is same as 10 to the power minus 1 if you apply your indices, times 6.02 power 23. So that becomes 6.02 times 10 to the power 23. Add these two numbers, multiply, then add their powers. That becomes minus 1 plus 23. Adding, taking one base and then adding their powers. That becomes 6.02 power 22 atoms. So we have 6.02 power 22 atoms or silver in 10.8 grams of silver bracelet. So we take another example. So next example says calculate the number of atoms of argon present in 3.84 times 10 to the power minus 3 mole of the gas. In this question, the number of moles is given to us as 3.84 power minus 3 moles. So we are not finding the number of moles of argon. We're looking for the number of atoms, which we take as NS, number of atoms. So this is a straightforward question. To find the number of atoms, we have NS equal to mole times Avogadro's constant. Number of moles given to you already as 3.84 power minus 3. Avogadro's constant 6.02 times power 23. So when we solve this by pressing our calculator, we have our final answer as 2.31 times power 21 atoms. 2.31 power 21 atoms of argon present in this mole. So having done that, having done justice to how to calculate the number of atoms, relationship between number of atoms and mole, we'll now move over to how to calculate number of molecules using the same equation number 4, number of molecules. So let's look at the question on the board that says calculate the number of molecules present in 14 grams of nitrogen gas. Now, the mass of nitrogen gas is 14. We have to first of all find the number of moles of nitrogen in these 14 grams. So nitrogen is a molecule. We'll do for the molecular mass. Nitrogen is the atomic. So that becomes 14 multiplied by this 14, not this one. Atomic mass multiplied by 2, which is 28. So number of moles of a molecule given by mass over molecular mass or molar mass, which is substitution 14 grams over 28. That gives you 0.50 mole of the gas. So you see our Pleasant equation NS for number of molecules equal to mole times Avogadro's constant. This time around, your S doesn't represent atoms. Your S now represents molecules, the number of molecules, even though the same formula we're using. So that becomes substitution 0.5 number of moles times the Avogadro's constant, which is in bracket. That gives us 3.01 times 10 to the power 23 molecules of nitrogen in this 14 gram of the gas. So that's the answer to the question. We'll take another example on number of molecules before we go to number of ions. We'll look at the question on the whiteboard that says calculate the number of molecules present in 5 grams of argon gas. So this question is similar to that of nitrogen that we did some few minutes ago. So in this question, the mass of argon is 5 grams. We'll look for the number of moles of argon first. Number of moles is given by mass over atomic mass. Why did I use atomic mass for argon? Because argon is a monatomic gas, is a noble gas. So it does not exist as a molecule. Unlike nitrogen that we multiply by 2, 14 by 2 in the previous example. So argon is monatomic. So I stated this in the earlier part of the video. So mass is 5. This is 40 mass, which is 0.125 mole of argon. So you're looking for NS, number of molecules, which is mole, times Avogadro's constant, which is 0.125, number of moles you obtain, times 6.02 power 23. So when we multiply this and solve that, our final answer becomes 7.53 times 10 to the power 22 molecules. That's our answer. 7.53 times 10 to the power 22 molecules of argon. So we'll now go to calculations that will involve number of ions, which is a little bit complicated. So move over to calculation number of ions. We have that question on the board that say calculate the number of chloride ions present in 5.55 gram of calcium chloride solution. Calculate the number of chloride ions present in 5.55 gram of calcium chloride solution. So let's start solving this problem. What do we do? We're given the mass of calcium chloride, which is the compound. So mass of calcium chloride, they call it MCaCl2, is 5.55 gram. You need to find the molar mass of calcium chloride. It's given to you already. So the molar mass is given to us already. We don't need to calculate it 1 gram or the molecular mass. So having done that, since we have mass and the molar mass of the compound, we find the number of moles of this substance. Number of moles of calcium chloride is mass over molar mass, which is 5.55 all over 111. And that will give us 0.05 mole of calcium chloride. So we obtain the number of moles of calcium chloride. So what else are we going to do? Perhaps what will come to your mind, you say number of ions is mole times Avogadro's constant. You substitute and then solve. If you do it, you're wrong. That is not correct. Because this is the number of moles of the compound. But the question, our interest is on calcium chloride. Calcium chloride. So our interest is on chloride ions, sorry. But what we obtain is the number of moles of the compound. So our interest is on chloride ions. So what do? We need to ionize the compound. So I repeat, what we calculated was the number of moles of calcium chloride. So to apply this formula now and substitute here as 0.05 times 6.02 to get the number of chloride ions is very wrong. Because this does not represent the number of moles of chloride ions, rather this is the number of moles of calcium chloride. And we have to find the number of chloride ions. So we have to find the number of moles of chloride ion. So this is for calcium chloride. So what do we do? We're going to ionize this compound so that we can bring out chloride ion. Because if this compound does not ionize the solution, you cannot bring out chloride ion from it. So let's see. We'll move on. To ionize the compound, one more of the compound, calcium chloride, will split to give us calcium ion and then chloride ion. So balance the equation. Because here is 2, you have to put in front of chlorine. Connect the calcium chloride to the chloride ion. You don't have business with calcium. Now have 1 mole of calcium chloride. Produce, this is 2 moles of chloride ion. From our previous calculation, the number of moles of calcium chloride calculated from this is 0.05. When I say 0.05 mole of calcium chloride, we now produce 0.05 times 2. That gives us 0.10 mole of chloride ion. So this is the number of moles of chloride ion, which is 0.01 mole. 0.10 mole. So having obtained this now, we can now find the number of ions. Number of ions by this formal equation, mole times Avogadro's constant. We now apply here 0.1 mole, which is the number of moles of chloride ion, then times the Avogadro's constant, 6.02 power 23. And that gives us 6.02 power 22 chloride ions as our final answer. So having done that, we're going to take another question. So look at the problem on the board that says calculate the number of hydrogen ions present in 200 cm cube of 0.1 molar solution of H2SO4. Calculate the number of hydrogen ions present in 200 cm cube of 0.1 molar solution of H2SO4. So this question is more like the previous one because we're looking for number of ions. And then in the previous one, we're given the mass of the substance, but in this one, we're given the volume and concentration. All the same, we're going to say find the number of moles of the substance before we continue, of the substance which is H2SO4. So find the number of moles of H2SO4. In this case, I'm going to apply this one as CV over 1000 because we're giving the concentration, giving the volume in Cn cube. That's why you have 1000 there. And that will give us 0.1 times 200 all over 1000. So when we solve this, our number of moles will now become equal to 0.02. Our number of moles, 0.02 moles of the acid. So that is the value of the number of moles. Now, having done that, this is the number of moles of the acid, not the number of moles of hydrogen ion. So get hydrogen ion, we'll have to ionize the acid, which is H2SO4. To ionize it, you write the ionization or dissociation equation, break it into ions, remove hydrogen ion, then SO4, whose charge is -2. This 2 goes to SO4, take back the charge. This 2 is also put in front of hydrogen to balance hydrogen atoms. So having done that, we'll connect this acid to the hydrogen ion. 1 mole of H2SO4 produce 2 moles of hydrogen ion. In calculation, the number of moles of the acid calculated is 0.02. We'll now say therefore 0.02 mole of H2SO4 will now produce 0.02 times 2. That gives us 0.04 mole of hydrogen ion. So this is the number of moles of the hydrogen ion. We'll now do for the number of ions. Number of ions becomes mole times Avogadro's constant, which is going to be 0.04 times 6.02 power 23. Solving or working this out, our final answer becomes 2.41 times power 22 ions or hydrogen ions present in that solution. So having done that, we'll now move over to the 5th formula for finding number of moles. We have done 4 formulas. We have done mole equal to mass over atomic mass. We have done mole equal to mass over molar mass. Mole equal to CV over 1000. And then mole equal to NS over Avogadro's constant. We'll now go to the 5th formula. So we have the 5th formula on the board. But this formula connects number of moles of a particular state of matter, which is gas. Not solid, not liquid. The other formula we'll be looking for, the other formula we have studied could be for any state of matter. But this one is for gaseous substance. Ng, number of moles of a gas, equal to Vg, volume of gas, all over mvg at STP, which is Ng means number of moles of gas or volatile liquid. Then Vg is volume of gas evolved or liberated at STP, which is standard temperature and pressure. mvg means molar volume of gas at STP is a constant. That's why we have it under here. The value of that mvg is 22.4 dn cube or 22.4 liters, because 1 liter is what 1 dn cube, or 22400 cn cube. So this is the formula that connects number of moles of gas to its molar volume and its volume obtained at STP. So let's take a question here. So look at that question on the whiteboard that says calculate the number of moles present in 5600 cn cube of oxygen gas at STP, and in bracket we have molar volume of gas at STP to be equal to 2.4 dn cube. So how do we solve this problem? Look at this problem. You are given the volume of the gas at STP, Vg, which is 5600 cn cube. So which we want to convert to dn cube. Okay, let's go down. What we have here is the molar volume of gas at STP, which is 22.4 dn cube. So you see that these units are not uniform. So either you convert this one to cn cube or you convert this one to dn cube. Anyway, will work out. In dn cube, divide by 1000, that gives you 5.6 dn cube. in Cn cube multiplied by 1000. That gives you 22400. So make the units uniform. Number of moles of gas given by the volume of the gas all over molar volume, which is of course 22.4 dN cube at STP. So the volume of the gas is in dN cube is 5.6. The molar volume is 22.4, also in dN cube. So the units are now uniform, they cancel out. So that gives us 0.250 mole. If you prefer to work in Cn cube, it's still okay. Number of mole becomes volume in Cn cube is 500 Cn cube. While this one in Cn cube multiply by 1000, that gives you 22400 Cn cube. So you now have 22400. To solve, you still have the same 0.25 moles. So whichever way you want to follow, you see arrive at the same answer. So the next, we are now going to combine our formulas. Combination of the formulas for moles. Now, if you look at the whiteboard, on the left-hand side of the whiteboard, we have the formula for number of moles we obtained today. Mole, mass over atomic mass, equation 1. Mole, mass over molar mass, equation 2. Mole, concentration and volume over 1000, the volume is in Cn cube, equation 3. Or CV, the volume is in dN cube. Number 4, mole, NS, number of particles over Avogadro's constant. Number 5, number of moles of gas, the volume of the gas at STP all over the molar volume. Now I can combine any of these two to get another form of equation, depending on what I'm looking for. For instance, if you go to the right hand side of the board, if I combine equation 2, mass over molar mass, with equation 3, CV over 1000, I have this, because this is mole, equation 2 is mole, 3 is mole, so the two of them should be equal to each other, depending on what I'm asked to calculate. Because I'm asked to do for mass, I have concentration, have volume, have molar mass. I can join the two of them together. Then look at if I combine 1 and 3, 1 and 3, sorry, it should be 1 and 4. 1 mass over atomic mass, and 4 number of particles over Avogadro's constant. I have this equation 4 to look for any missing item where other ones are given. If I combine 2 and 4, mass over molar mass equal to NS over NA. That is it. Then if I combine equation 2 and 5, 2 and 5, I will have equation 2, mass over molar mass, then 5, which is volume of gas all over the molar volume of gas. So that means all these equations are equal to each other because they represent number of moles. So depending on what is given to you in the equation, you can join the two of them. Let's assume that one item is missing and other ones are given to you. Then you can join the two and find the missing item. So this is combination of the mole equations. You can relate any two mole equations and then solve for the unknown. So let's go to an example or two examples to illustrate this. So let's look at the question on the board that says, what mass of sodium carbonate is required to prepare 250 Cn cube of 0.1 molar solution? What mass of sodium carbonate is required to prepare 250 Cn cube of 0.1 molar solution? So it says again, what mass of sodium carbonate is required to prepare 250 Cn cube of 0.1 molar solution? So from the information given to us, the volume of the carbonate is 250, of the solution is 250 Cn cube. The concentration is 0.1 molar or 0.1 mole per dN cube. This is the molar mass given to us. So the molar mass of the substance is 106 gram per mole. We're looking for mass of the mass required to prepare this concentration. Now, if you look at the information given to you in this question, you see that if you combine C and V, you get N, CeV over 1000. And that will only give you number of moles only. You're looking for mass. You also know that number of moles is mass over molar mass. Since you look for mass, mass is not found in this equation but found in this. So you can connect the two of them together and now have mass over molar mass, CeV over 1000. You cross multiply and make mass the subject. So mass becomes equal to CeV times molar mass over 1000. You walk straight and get the answer speedily. The mass is, okay, we're making mass the subject. So mass, okay, C becomes substitution 0.1. Molar volume is 250. Molar mass of the compound is 106 over 1000. To solve this, the mass required is 2.65 grams of sodium carbonate to prepare the given concentration. So look at the problem on the board that says calculate the weight of 11,200 cm cube of nitrogen gas at STP. The weight of 11,200 cm cube of nitrogen gas at STP. So to solve this problem, we're looking for weight. And here, weight connotes mass in chemistry. So we're given volume. Volume here of the gas is 11,200 cm cube at STP. We're also given the molar volume of the gas at STP is a constant, 22.4 dn cube. These units are not uniform. I'll convert this to dn cube by dividing by 1,000. That gives me 11.2 dn cube. By dividing that by 1,000, I have 11.2 dn cube at STP. So having done that, we're looking for the mass, because weight, we are not looking for force gravity, not physics. So we have to find weight in chemistry. We're talking about mass. So we'll now look at this question. What are we looking for? We'll have the atomic mass of nitrogen, 14. So that is the molecule. So find the molar mass of nitrogen molecule, or the molecular mass, N2. It's not a noble gas. So multiply it by 2. That gives you 28. So if you look at these two are connected to mole by the formula mole of a gas given by volume of gas all over 22.4 dn cube. But we're not looking for volume. We're not looking for mole either. We're looking for mass. And also look at mass and this, the connection mole again by mass over molar mass. Between mass and molar mass and mole. So this is mole, this is also mole. The two are equal. You equate volume of gas all over 22.4 dn cube, which is mole, again as mass over molar mass. You cross multiply and make mass the subject. So mass becomes equal to volume of gas times molar mass all over 22.4 dn cube, making sure that the volume is in dn cube as we did before, converted. So we now have 11.2 times 28 all over 22.4, making substitution now. The mass of the gas is going to be 14 grams of nitrogen gas, or 14.0 grams of nitrogen gas. That is the answer to the question. So let's look at the question on the board that says calculate the weight of 4.92 times 23 atoms of gold. And you're given in bracket the atomic mass of gold as 197 and then the Avogadro's constant as 6.02 per 23. So how do we start? The number of atoms given to us as NS, 4.92 per 23 atoms of gold. The Avogadro's constant given to us as 6.02 per 23. The atomic mass of gold is 197. Gold is a metal, and metals are monatomic, so you don't need to multiply this by 2. It's a metal, monatomic element. Remember what I said at the beginning of this video. So having done that, you're looking for weight, which refers to mass. Now, if you look at these two items, mole given by number of particles over Avogadro's constant. But you are not looking for mole, you're looking for mass. Look at these other two items. Mole is given as also mass over atomic mass. So you can connect them together. Then all you have to do is to cross multiply and make mass. The solid mass becomes equal to number of atoms times Avogadro's atomic mass all over Avogadro's constant. So number of atoms, particles is 4.92 power 23. Then atomic mass of gold is 197. Avogadro's constant is 6.02 power 23. 23 cancels 23. We'll now solve out and get the answer. When we solve, our final answer is 161 grams of gold. That becomes the final answer to this question. So having done that, now we're going to the next session that involves solving miscellaneous exercises, solving different problems on the mole concept. So let's critically look at this question on the board and understand it before we solve it. It says that black gunpowder contains several elements, among which include sulfur and carbon. A sample of the powder contains 10.09% of sulfur by mass and 14.29% of carbon. Calculate the number of moles of sulfur and carbon in 1 pound of the powder. I repeat, black gunpowder contains several elements, among which include sulfur and carbon. A sample of the powder contains 10.09% of sulfur by mass and 14.29% of carbon. Calculate the number of moles of sulfur and carbon in 1 pound of the powder. In bracket, you're given the equivalent of 1 pound, which is 454 grams, and they're given the relative atomic mass of sulfur and carbon, which are 32 and 12 respectively. So how do we solve this problem? To solve it, we'll start with a carbon. Okay, the one mentioned first is sulfur. So percentage of sulfur in the compound is, in the powder, is 10.09%. So all we have to do is to find the mass of sulfur in that powder, in the 1 pound weight of the powder. To find the mass of sulfur, I will now do mass of sulfur will now become percentage of sulfur all over sulfur times mass of powder or gunpowder, GP, gunpowder. So the sulfur percentage is 10.09 over 100. The mass of the gunpowder is 1 pound weight. And 1 pound is equivalent to 454 grams times 454 grams over 1. That gives me the mass of sulfur in the gunpowder. When I solve this, I'll be getting 45.81 grams of sulfur. You see that? So we have to find the number of moles of sulfur, which the number of moles is given by mass over atomic mass, since we consider sulfur as being monatomic, not a gas. So the mass of sulfur is 45.81. The atomic mass of sulfur is 32 given to you in bracket. So we'll divide. The number of moles of sulfur is obtained as 1.43 moles of sulfur in the gunpowder. So having seen how that was done, we can now look for that of a carbon, same process or same procedure. So to find that of carbon, replace this with percentage of carbon, which is here 14.29% of carbon. Mass of carbon in the powder, because percentage of carbon times mass of gunpowder, which should be 14.29 over 100 times 1 pound weight, which is 454 grams. When we multiply this, the mass of carbon will give us 64.9 grams. 64.9 grams of carbon in the gunpowder. Now, the number of moles of carbon becomes the same formula. So carbon being monatomic, 64.9 over atomic of carbon, which is 12 given to you in bracket. So we'll divide and solve. Our final answer becomes 5.41 moles of carbon as our final answer. So you see how this was done. So look at another problem. So let's look at the question on the whiteboard. An average sample of coal contains about 3.0% by mass of sulfur. How many moles of sulfur are there in 1.0 ton of coal? And in bracket, we're given some conversion units. 1 ton is 2,000 pound weight, and 1 pound weight gives us 454 grams. So what we're going to do is, since we have 1 ton here in the equation, that means the mass of coal is 1 ton, and 1 ton is for 2,000 pound weight from this. So having done that, let's find the mass of sulfur in the coal. So mass of sulfur in the coal become percentage of sulfur times mass of coal. So that becomes 3%. That is 3 over 100. The mass of coal is 2,000 times 2,000 over 1. And remember that we are working in pound in this. So after this, we'll now get 60 pound weight. So before we proceed to find the number of moles of sulfur, how to convert the 60 pound weight to grams? So how to convert to grams? We'll look at the conversion factor. 1 pound weight is 454 grams. So 1 pound weight is 454 grams. So 60 pound weight becomes 60 times 454. And that will give us the value of 27240. That is 27,240 grams of sulfur. So having done that, the number of moles of sulfur is mass over atomic mass, which is going to be 27240. The atomic mass of sulfur is approximately 32. So when we solve, we'll have our final answer, which is 851.3 moles of sulfur present in 1 ton of coal. We'll go to the next question. So we have a question on the board that says a piece of platinum foil 0.254 millimeter thick and 50 millimeter by 50 meter sells for $525. How many moles of platinum are you bringing? The density of platinum is 21.45 grams per cm cube. The relative atomic mass of platinum again to you as 195.08. I repeat, a piece of platinum foil 0.254 millimeter thick and 50 mm times 60 mm sells for $525. How many moles of platinum are you bringing if the density of platinum is 21.45 grams per cm cube? To go to the equation, we are given the dimensions of the platinum foil. This is the thickness. The thickness is 0.254 millimeter. We're also given the dimension. 1 will be the length. So and 1 will be the breadth. That means the platinum has a square kind of shape because the length and breadth are equal. Then we're also given the density of platinum. They call it D as 21.45 grams per cm cube. What I would have to look for number of moles. Number of moles will always be given by mass all over. Because platinum is a metal, I'll use atomic mass, being monoatomic. So that means if I solve this problem, I have to find the mass of platinum. And then atomic mass is already given to us with all this information given to us. Then for us to find mass, you see that From this information given to you, the units are not concord, are not in accordance. This is cm cube, this is millimeter, millimeter, millimeter. So what I'm going to do is, I'm going to harmonize the units. I'm going to bring the millimeter to cm, centimeter. By dividing each of them by 10, that'll give you 0.0254 cm. Divided by 10, that'll give you 5 centimeter. Divided by 10, also 5 cm. Because 10 millimeter make 1 centimeter. So convert each of them to cm and divide all of them by 10. So having done that, I have density. I want to find my mass. Remember that from your physics or physical chemistry, density is mass over volume. So mass should become density times volume. So before we go ahead, we have to find the volume of the platinum foil. To find volume, we apply the formula breadth times length times thickness. So you multiply the breadth, length, and thickness, get the volume. And I have 5 times 5 times 0.0254. That gives us the volume of the platinum foil. And you multiply that to get 0.635. 0.635 cm cube. So having done that, we can go ahead and solve our density. Mass is density times volume. Density is in bracket, okay, is 21.45 gram per cm cube. Volume is 0.635 cm cube. Cm cube cancels cm cube, so the mass is now being gram, which is what we want. So we'll multiply out the mass we're going to get is 13.6 gram. 13.6 grams as our mass. So applying this formula now, mole, mass or molar mass. Our mass is 13.6. The mass of platinum is 195.08. When we divide, we get the number of moles of platinum in the foil, which is 0.0697 mole as our final answer. Look at this question on the board that says, calculate the percentage composition of an organic compound with the molecular formula C4H8O. In this question, what it means is that we should find the percentage of each element in that compound. So we have to find the percentage of carbon, hydrogen, and oxygen in this compound. What do we do first? We first find the relative molecular mass or the molar mass of that compound, which is C4H8O. That becomes 4 times 12 for carbon. The mass is 12, and there are 4 atoms here. Hydrogen is 8 times 1, 8 atoms. That's total mass is 1. Oxygen is 16, which is only 1 atom. We now have 48 plus 8 plus 16. That gives you 72. So let's start with the first element, carbon. So the mass of carbon in 1 mole of the compound becomes 12 times 4 because of 4 atoms. That becomes 48 grams of carbon. So percentage of carbon becomes mass of carbon 48 over the molar mass of the compound 72 times 100 over 1. And that will give us the answer. Carbon gives us 66.7% for carbon. We'll now go to the next element, hydrogen. Mass of hydrogen in the compound, or in 1 mole of the compound, becomes 8 times 1, 8, because there are 8 atoms of hydrogen, and atomic mass of hydrogen is 1. So percentage of hydrogen becomes mass of hydrogen, which is 8, over the molar mass, which is 72, times 100 over 1. So when we solve it, our answer will now become, for hydrogen, will now become 11.1% of hydrogen in the compound. So we'll now move to oxygen in the compound. In oxygen, the mass of oxygen in the compound, oxygen is only 1 atom and is 16, so the atomic mass. So percentage of oxygen becomes 16, but the molar mass of the compound, which is 72, times 100 over 1. When we solve this, our final answer is going to be 22.2%. To check whether you are correct, add the whole percentages. It's 66.7 plus 22.2 plus 11. You're going to get 11.1. You're going to get 100%. You're going to get 100%. That shows that the question or the solution is correct. So I have a question on the board that says an organic compound contains 40% carbon, 6.67% hydrogen, and the rest is oxygen. If the vapor density of the liquid is 30, that the compound is a liquid, determine its 1 empirical formula, 2 molecular formula. So let us start with empirical formula. Empirical formula is the formula of a compound which shows the atoms present in one molecule of the compound in their smallest ratio. The formula of a compound which shows the atoms present in 1 mole of the compound in their smallest ratios. That's the empirical formula. So let's go ahead to solve this first one, empirical formula. Let me call it EF. The first thing I'm going to do is to list the composition of the compound. The composition will have carbon 40%, hydrogen 6.6%, oxygen, we don't know the percentage. Since it's a complete compound and the sum of a percentages will be 100%. To get that of oxygen, I will call it S. How I get it? It's going to be 100 minus the sum of 40 and 6.67, the remaining composition. So if you add 46.7, 100 that will give you around 53.3%. So having obtained the percentages, the next step is divide each with the relative atomic mass of the elements. Carbon mass is 12 divided by 12. Hydrogen, the mass of hydrogen is 1 divided by 1. Oxygen, divide the mass of oxygen is 16. All the values should have been given to you in the bracket. The omission, so you have to know it. So having done that, divide it to give you 3.33, 6.67, 3.33. We obtain the number of moles. Which number of moles? Then the next thing is divide with the smallest mole. So out of the 3 values, the smallest mole remains 3.33, even though it occurred 2 times. Even if they are all different values, divide all of them with the smallest value. So you have 3.33 all over 3.33, 6.67 all over 3.33, 3.33 all over 3.33. Whatever you get, approximate to the nearest number. They will give you 1, they give you approximately 2, they give you approximately 1. If it's 2.5 you're getting, then the answer would have been 3 here. But we're having 2.0 something, so this is 2. So the empirical formula now, what do? You assemble the elements, carbon, hydrogen, and oxygen, the 3 elements here. Ratio of carbon is 1, hydrogen 2, oxygen 1. That will give you CH2O as your empirical formula. So this is how you calculate the empirical formula of a compound when you're given the percentage composition of the elements in a compound. So we have done justice to number 1. We'll go to number 2. Number 2 says, find the molecular formula. What is molecular formula? Molecular formula is the formula of a compound which gives the actual number of atoms. The actual number of atoms in one molecule of a compound. So, to find the molecular formula, we call it MF. The first you have to do is to find the empirical formula, which we have done previously as CH2O in question 1. The next is you multiply the empirical formula by a factor, which I will call N. Multiply the empirical formula by N and make it equal to the molar mass or the molecular mass of the compound. So, we are getting the empirical formula. So we're going to make it equal to the molar mass of the compound. So how to look for the molar mass of the compound? You go to the question, they told you that the compound has a vapor density of 30. So they did not give us the molar mass. So either we use the molar mass or use the molecular mass. So since they gave us the vapor density, we cannot use this in place of the molar mass. The relationship between molar mass and density is molar mass given by 2 times vapor density. This is a constant. That relationship between the two of them. So since the density is 30, molar mass becomes 2 times 30. That gives us 60 as our molar mass. So go back to this. Replace the EF with CH2O bracket N equal to 60, which is the molar mass. Having done that, the next you do is you find the molar mass of the empirical formula. By substituting the values with the atomic masses of carbon, carbon is 12, hydrogen is 1, multiplied by 2 because of 2 atoms, oxygen is 16 for 1 atom only. That's all these are given to you, N equal to 60. So 2 times 1 is 2, plus 12, 14. 14 plus 3 is 30. And I have 30N equal to 60. My N now becomes 60 over 30. My N becomes 2. So N is normally or usually a whole number. So when you have done that, we now go back to this expression, which is CH2O, and replace N with 2. We now have CH2O multiplied by 2. That gives you C2H4O2. 1 carbon inside times 2. Bring the 2 down as subscript. 2 times 2 gives you 4. 2 times 1 here gives you 2. So this is the molecular formula of the compound. And because it's an organic compound, if you are good in organic chemistry, you know that this compound here is written as CH3COO if you bring out the functional group. Because you have 1 and 1 carbon, 1 plus 1 gives you 2. 3 hydrogen plus 1 gives you 4. 2 oxygen atoms, so these two are the same thing. So that is it. So I have this question on the board that says 1.51 times 10 to the power 22 atoms of S weigh 2.94 gram and 0.112 mole of Y weighs 3.23 grams. S and Y combine to form a compound which contains 3 atoms of S and 2 atoms of Y. Question A. What is the simplest formula of the compound? B. What is the atomic mass of S? C. What is the percentage composition by weight of the compound? Let's start with question A. Question A is asking us the simplest formula of the compound. And the simplest formula of the compound is called the empirical formula. You look at the last sentence, you say S and Y combine to form a compound which contains 3 atoms of S and 2 atoms of Y. So solution to A is simple. The ratio of atoms in S to Y is 3:2. 3 atoms of S and 2 atoms of Y. So the simplest one of the compound form is nothing but S3Y2. That is the answer to question A. Number B says we should find the atomic mass of S. To find the atomic mass of S, we should go back to the equation and then look for information or clue to solve this. We are given the number of atoms of S. The number of atoms of S, NS, is 1.51 power 22 atoms of S. And then they say that these atoms weigh 2.94. So the mass of S is 2.94 gram. And we're looking for the atomic mass of S. How do we go about it? We know that mole is given by mass over atomic mass. We don't know mole. So we're looking for atomic mass. So you cannot look for 2 things in the equation. And also remember I told you the same mole is given by number of atoms over Avogadro's constant. So you can see that. So this is mole, this is also equivalent to, so you can equate the two of them together. The mass is given to you. The atomic mass of S is what you're looking for. The number of atoms, you know that. Avogadro constant, you know that. So you're looking for one item here, which is the atomic mass. So you cross multiply and make AM the subject. AM becomes equal to mass times Avogadro's constant all over mass times this all over mass times Avogadro's constant all over number of atoms. So the mass, let's work it here. The mass of the S is 2.94 grams of S times the Avogadro's constant, we know it is 6.02 power 22 all over, then the number of atoms, which is 1.51 times 10 power 22. This is 23, please, for Avogadro's constant. So when we solve this, we have our answer as 117, approximately 117 as the atomic mass or the relative atomic mass of S as the answer. We'll go to number C that says we should find the percentage composition by weight of the compound. Before we do that, we need to find the relative molecular mass of the compound. So let me write this. Number C, I'll find the molar mass or molecular mass of the compound, which is, the formula is S3Y2, which you got in equation 1. So for us to solve that. But before we go ahead to do that, we need to first of all find the atomic mass of Y, because you cannot find the molecular mass of the compound without knowing that of S, that of Y, even though we're getting S as 117. So atomic mass of S is, let's write it down here, of S is 117. We need to evaluate that of Y before we find the molar mass of the compound. So to find out of Y, we go to the information given to us. The number of moles of Y is 0.112 mole of Y, and then the weight of Y or mass of Y is 3.23 grams of Y. So let's find the atomic mass of Y. Remember, the number of moles is mass over atomic mass. Make this the subject. The mass becomes mass over mole. The mass of Y is 3.23. The number of moles is 0.112. So you now find the atomic mass of Y first, and that'll give you 28.8. So we have obtained the atomic mass of S as 117, and that of Y as 28.8. We now find the molecular mass, yes, you can go ahead now, of S3Y2, which is 3 times 117 for S, 3 atoms, the atomic mass of S, plus 2 times 28.8 for what? Y. The mass of Y is 28.8, and there are 2 atoms. So you find the molar mass of that molecule. When you solve it, your answer is going to be 408.6. 408.6. That's the molar mass or molecular mass of the compound. So we're looking for the percentage by weight of the compound. That means we're going to find the percentage of S in the compound and the percentage of Y in the compound. So to find the percentage of S in this compound, S3Y2, now find the mass of S in the compound. So mass of S in the compound is in S3Y2. Will now be, there are 3 atoms of S. That becomes 3 times the mass of S, which is 117. So we find the mass of S in the compound, and that will give us around whatever value, multiply, we'll have it. This is 21, carry 2, 5, 351 grams. That becomes the mass of S in the compound. So percentage of S in the compound becomes the mass of S all over the molar mass of the compound S3Y2 times 100 over 1. And that will give us, of course, the mass of S is 351 The mass of the compound is, got it today, 408.6 times 100 over 1. When we solve this, we have our final answer as 85.9%. 85.9% of S. So, to find the percentage by weight of Y, the same process, you find the mass of Y in that compound, the mass of Y in the compound here. So, mass of Y in S3Y2 becomes 2 times 28.8. 28.8, remember, we got the other mass of Y. That gives us 57.6 grams. So percentage of Y becomes mass of Y all over the molar mass or the molecular mass of the compound, which is S2Y3 times 100 over 1. That becomes 57.6 all over 408.6 times 100 over 1. That gives you the mass of Y in the compound. When you solve that, the answer becomes 14.1% of Y in the compound. To verify whether you're correct, since the compound contains 2 elements, if you add this percent of S to that of Y, you should be getting 100% to show that you are on the right track. So that is it. So let's look at the question above that says calculate the mass of oxygen in 120 grams of SO2. Calculate the mass of oxygen in 120 grams of SO2. So how do we solve this problem? The mass of oxygen in 120 grams of SO2. So what I have to do is this. We're going to find the percentage of oxygen in this compound. We'll start by finding the relative molecular mass of SO2. So with these values given to us, the relative mass of sulfur is 32, oxygen is 16 multiplied by 2 because of 2 atoms. That gives you 64 at the relative molecular mass, or 64 grams per mole at the molar mass of SO2. Then we look for the mass of oxygen in this. So mass of oxygen in this compound becomes 16 times 2 because there are 2 atoms of oxygen. That gives you 32 grams of oxygen. So the mass of oxygen in that 120 gram becomes in 120 grams of SO2 will now become the fraction of oxygen, or we'll put it this way, mass of oxygen in 1 molecule of SO2 all over molar mass of SO2 times 120 grams over 1. So the mass of oxygen is in 1 molecule of this is 32. The mass of SO2 is 64 times 120, and that gives you 50 grams of oxygen in 120 grams of SO2. So that is it. So we're taking one more last problem for today's lecture that will round off the mole concept. So the question says calculate the number of atoms present in 3.2 grams of sulfur 4 oxide or sulfur dioxide. Calculate the number of atoms present in 3.2 grams of sulfur 4 oxide. So we'll start. This is the molecule. Find the molar mass or the molecular mass of SO2 first. We'll do that. With the values in bracket. Sulfur 32, oxygen 16 multiplied by 2 because of the 2 atoms there. That gives you 64. Having done that, we'll find the number of moles of SO2 present in 3.2 grams. Number of moles given by mass over molecular mass, which is 3.2 over 64. And that gives us 0.05 mole of SO2 present. So the next we'll do is to find the number of molecules of SO2 in this 0.05 mole. number of molecules which can be tagged as NS given by number of moles times Avogadro's constant. That becomes 0.05 times 6.02 times power 23, which we are seeing there. So when we multiply this, we'll be getting the value, we'll be getting a 3.01 times power 22. 3.01 power 22 molecules of SO2 present in 3.2 grams. Having done that, the next we'll do is we'll ask ourselves how many atoms, go look for number of atoms, how many atoms are in one molecule of SO2. In one molecule of SO2, we have one atom of sulfur and 2 atoms of oxygen. And that gives us 3 atoms. So the total number of atoms in this number of molecules calculated becomes the number of atoms 3 times the number of molecules of SO2, which is 3.01 times power 22. That gives us 9.03 times 10 to the power 22 atoms of SO2 present. So that is it. We've done justice to today's lecture. So finally, we have done justice to today's lecture on mole concept. With all these illustrations we have done, I believe we can tackle all problems involving mole concept. So this lecture is comprehensive or well packaged in that we started from the scratch so that those in high school, even in SS3, can follow this lecture up to those in year 1 and those who are doing their JUPEB program. So this is a comprehensive lecture on mole concept. In our next lecture on general chemistry, we shall be going to stoichiometry of reactions, which is somehow connected to the mole concept, whereby we work to calculate the mass of reactant or mass of product formed in a chemical reaction, or volume of reactant or volume of product liberated if it's a gas in a chemical reaction, the stoichiometric reactions. So that'll be our next topic on general chemistry, which we are treating now. And then after that, we'll now go to chemical bonding, with the last aspect of general chemistry, which takes some time for us to finish. So if you are watching this video for the first time, as I said, subscribe and then share the videos. Share it out to somebody in need, be it in your own university or in a different university altogether. You can share the video out and then help someone in need. So thank you very much and remain connected.